Chat with Traders, collaboration with Quantopian, episode 5. Hey, how's it going, folks? Aaron Fifield here of Chat with Traders podcast. What you're listening to right now is part 5 in a special 6-part series, which is, of course, a collaboration with the good people at Quantopian. In this episode, we explore machine learning in trading and in finance. We talk about what is machine learning, where it's commonly used in everyday life, and what are some of the good and not so good ways that quants may use machine learning. Joining myself and Delaney is Max Margenot. Max is a data scientist at Quantopian, and needless to say, he knows a lot about the subject matter. Just to run through a few things real quick, if you have any questions, please go to quantopian.com/questions. That's where you can go to submit any questions that you'd like answered on the 6th episode. For a full list of resources mentioned during this episode, simply visit quantopian.com/chatwithtraders. You'll find everything there all in one place. And also, props to DataCamp for sponsoring this series. As I've been preaching, datacamp.com, in my opinion, is probably the best place you could go to learn how to program, particularly for working with data in languages Python and R. Their courses, some of which are entirely free and taught by talented data scientists, are very interactive. There's videos, there's coding tasks, and much more, all of which you can complete online using their portal. Really good stuff. So visit datacamp.com today, sign up for a free account, and get stuck into one of their online courses, which cater for programmers of all levels, beginner through to intermediate. Again, that's datacamp.com. Last thing I should point out to you is the next episode and the final episode in this series is the Q&A episode. So these episodes have been coming out weekly, but I'm not exactly sure when this next episode will be released. It's likely to be in January sometime though, but if you follow me on Twitter, I'll of course keep you posted. Anyway, let's get to it. Here is Delaney and Max Margenot to talk all things machine learning and trading. Delaney, here we are, episode 5. I'm excited to be doing this. We're discussing something very interesting today, machine learning. We're also joined by Max. Max, I'm not even going to attempt to pronounce your last name because I know even Delaney struggles with that one. So, Max, I'll leave that part up to you. But, tell us a little bit about your story. Give us a quick introduction and, just bring us up to speed with who you are and your experience in the field.
Yeah, so I'm Max Margenot. It's a tough one. But I'm a data scientist at Quantopian. I also help to manage the lecture series. I've done a lot of math and statistics in the past. I've messed around with a lot of like cryptocurrency stuff, a lot of trading bots on Bitcoin. Some of them involving machine learning, some of them not involving machine learning, but generally stuff that I found interesting that other people may or may not find interesting. So a lot of math, a lot of statistics stuff.
That's awesome. No, I think that's very cool. What attracted you to cryptocurrencies? Do you still muck around with that sort of thing?
Currently, I'm actually not allowed to, but what mainly drew me to them in the first place was I was a little involved with Bitcoin when they first started happening. I heard about it years and years ago, and I was like, all right, I'll mine some of this on my own computer. So I got into it then, and then I got back into it when I realized that the APIs for the online exchanges, the ways that I could get my bots and everything to communicate with them were very simplistic compared to actual trading, stocks or anything, APIs. So I was just all right, I'm going to build bots on cryptocurrencies because it's easier.
Okay. Awesome. So you actually got involved in the mining side of it as well.
Yeah, not super into it because this was back when I was still pretty terrible at computers, I guess. So I didn't really have a proper setup for it. It was just mining on my desktop computer, nothing special.
Okay. So what part do you play at Quantopian today? Tell us a little bit about that.
Yeah, so as part of the academic team, I am right on Delaney. I run a quantitative finance lecture series. So we basically have this curriculum of just curated IPython notebooks in our research environment. And we just kind of, well, we have a bunch of individual lectures on statistical concepts and financial concepts, building up from like the very most basic stuff, like how do we even use Python? How do we even use some very basic Python packages? And what is a mean or a variance or a standard deviation? Up through like actual examples of building trading algorithms, like pairs trading algorithms or long-short equity algorithms. So it's a pretty wide range of content.
Yeah. Delaney's referenced it many times during this series. So, anyone who's listening is aware that those lectures are all available. I think it's at quantopian.com/lectures. What sort of education do you have, like, to be doing this sort of thing?
Yeah, so I have a bachelor's in math, minor in computer science, and then I have a master's in mathematical finance.
Very impressive, man. All right, cool. Well, let's get stuck into it. So, first things first, at a very high level, what is machine learning? Many people have probably heard the term, but many people probably don't fully understand it as well. So, yeah, let's start right there. What is machine learning?
Machine learning is a really, really broad field, and it's also something that means many different things to many different people right now, I think, because it's such a young field. It's to an extent in its infancy, and there's so much excitement and, I call it a hype cycle around machine learning that everybody's excited about it now. And so there's tons of people trying to get into it. And you have all the people who have kind of been doing this forever being like, I don't understand what's going on. I have all these people I've never seen before in my house, and they're trying to do all the same things I usually do, but they're not doing it right. So it's kind of, it's crazy right now what's going on in machine learning. At its core, and kind of I'll give kind of my very broad definition of it. I'm sure Max will also have a different angle on it, but like at its core, I view machine learning as any kind of automated statistical process that attempts to find patterns in data. So when you talk about the work that statisticians do on a day-to-day basis, a lot of machine learning is really just an attempt to actually automate that work itself and have the machine run tests, the machine find patterns, the machine fit models. And there's like a ton of different ways you can do that. But do you think that's like about right? Or
yeah, I definitely agree with that. I think like the patterns is definitely the biggest thing. It's just like a class of algorithms, and how people actually implement them is going to vary.
Okay, sure. So while we're talking about this at a very high level right now, in what areas outside of finance are machine learning techniques applied? It might be helpful for people listening to this who are unfamiliar with machine learning to think about how it's used in sort of almost everyday life.
A good example of this is probably talking about credit card fraud detection. And that's not frog as in the animal, which I always say by accident, but credit card fraud is in someone stealing your credit card and using it for their nefarious purposes. And obviously this is like a huge industry, detecting credit card fraud. And obviously, because oftentimes banks or credit card companies have to take the hit if someone uses a card improperly, because a lot of them will have guarantees. Generally, if someone steals your card and uses it for an improper purchase, generally you can get that canceled, at least in the States. I'm not sure about, other regions of the world. So as a result, credit card companies have a very large financial incentive to reduce the amount of fraud that goes on. And one of the first ways to do that, and kind of a very kind of low cost algorithmic way to do that, is just to monitor the transactions that are made on the credit card and try to pick out which transactions might be fraud. And so for people who have been listening to the previous podcasts, you might actually remember that we talked about classifiers a few different times. And so we're actually going to return to that notion, because what's happening here is a classification problem. You have in front of you a credit card transaction, and you would like to classify it as fraud or not fraud. And so, in fact, this is actually a special case of binary classification. I think we also mentioned this notion of binary classification being a very simple form of classification in which you only can classify into one of two buckets or outcomes. And so there's a lot of different machine learning algorithms that are used for this. And again, it's all about trying to find what patterns represent normal use. So you might have a machine learning algorithm that tells you, oh, well, the patterns that represent normal use are transactions with a mean amount of $20 and a standard deviation of $30, and they generally happen between the hours of 9 a.m. and 9 p.m. Eastern time for this user. And then you have all sorts of other details, right? Because in each transaction, you have the amount, you have where it was made from, how it was made, online or in person. You have the time it was made, assumingly, usually you also have the time zone in which it was made, probably one or two other things like whether it was swiped or on chip. And so you have basically for each transaction a bunch of little measurements, and the algorithms look through those measurements and they try to assign a likelihood to the overall transaction based on like how weird those measurements are. And so there are many different machine learning algorithms that could do something like this, but this general notion of classification is a core to a lot of machine learning. And I think that this is a good illustration of one of the common uses. Do you have anything to add to that?
Yeah, I mean, so it sounds like what you're talking about is definitely like an example of what we'd call supervised machine learning. Because you can usually break out machine learning methods, all these different algorithms, into a couple different classes themselves. This is supervised and unsupervised machine learning. So in supervised machine learning, what you do is you essentially hold the algorithm's hand. You'll show it, hey, here's all this data, and this is what it is. It's like I have this transaction at this time and all this, and this is fraud. Or I have this transaction at this time from this vendor, and this is not fraud. So you're in essence teaching it what is and isn't fraud by holding its hand through a bunch of different examples. And then you use that trained model to predict stuff in the future.
Okay, so what is unsupervised learning? Just, going to the other side of the spectrum.
So that's more when you just take all this data and you let the machine go ham. Like you just have an algorithm and it looks for patterns. It doesn't know what it's looking for. Nothing's really particularly labeled. This could be something like using the semi-essential example of credit card fraud, right? There's some whole collection of behavior, right? And at some point in this behavior, there's a shift. So someone, and we basically would hypothesize that there are two people or multiple people using the same credit card, right? Where we have this initial person, their initial behavior, and at some point the behavior changes. And that would be kind of a warning thing. And that's not really looking at what is or isn't fraud. That's looking for some sudden burst in purchases or some sudden new information that we haven't really experienced before that is outside the wealth of what we've already had to deal with. So that would be another way to market fraud instead of looking at individual transactions and marking them fraud or not.
I think a good, very simple, intuitive example of this might be that an unsupervised machine learning model might look at your credit card transactions and say 95% of your credit card transactions have a value of between $1 and $200, right? And so if you look at the value of a credit card transaction and it's outside of, it's above $200, that represents, kind of an uncommon event. It's a rare event. And that's some evidence towards the fact that it might be fraud. You probably wouldn't immediately flag it as fraud just because of that one occurrence. And so what another big thing that machine learning algorithms do is they usually try to kind of find patterns across multiple different variables. So in this case, one variable is the price, of the transaction. Another variable is the time at which it's made. And let's say for our purposes, a third variable is the location at which it's made. And so for each one, a machine learning algorithm might say, okay, well, 95% of transactions are between $1 and $200. 95% of them are made within 10 miles of this location, probably your home. And 95% of them are made between 9 a.m. and 9 p.m. Your time zone. And so if you see a transaction which is $300, but within 10 miles of your home and within 9 a.m. and 9 p.m. in your time zone, maybe that's not enough evidence to flag it. But then if you see a transaction which is $1,000 and it's 50 miles away from your hometown and it's 3 a.m. your time, that's a good amount of evidence that you want to flag it. So really what machine learning algorithms will do is try to find these patterns, try to figure out what is kind of normal behavior of these variables, and then look for examples which fall outside of those bounds.
Yeah, no, I think that's a really good summary. And I really do like the example of, credit card fraud detection. While we're talking about supervised and unsupervised machine learning, I don't know if this is maybe getting a little bit ahead of ourselves for where we want to be right now in this episode, but when is it right to use supervised versus unsupervised machine learning algorithms?
Well, it really depends on what you're going for, right? So if you have an idea of how things are, if you have an idea of the different classes that you're looking at, in credit card fraud still, you have fraud or not fraud. So if you know what your classes are going to be, then, well, there's really no harm in using a supervised algorithm where you're basically providing the inputs and you're providing the outputs at the same time and using this in order to train the model. But if you're looking for something, if you just have a bunch of unlabeled data and you want to learn something interesting about it, look for any particular clusters or different groups of behavior within this big data set. That's more of an unsupervised learning problem. So I alluded a bit to this kind of shift in behavior. So that's one way. That's one thing that we could learn about a data set just by running it through like something called a mixture model, right? If we don't know how many classes there are, but we suspect that there may be a few different things going on, what we would do is we would try to run it through a mixture model, which is an unsupervised learning algorithm, and see if it will group things into particular sections.
Okay, yeah, that makes sense. Now, Delaney, right at the beginning, you described, you said there's a lot of a hype around machine learning at the moment. I think you described it as being a hype circle.
A hype cycle, yeah.
Hype cycle. Why are people so excited about machine learning right now, particularly in the trading and investing space?
Well, I think there's a lot of reasons. I think machine learning is something that has been being developed in the computer science, math, and stats academic disciplines for, I don't know, maybe 30 to 60 years now, seriously. A lot of it has really just been enabled by modern computing. There's a lot of techniques that just would not be possible without kind of chips that were fast. And because, a lot of these machine learning methods take a lot of computational power. They require many iterations, many training cycles. So as a result, it's only kind of recently that it's really started to take off because consumer hardware has gotten fast enough to support machine learning algorithms. On the other hand, we're also in this, I believe, a hype cycle around kind of data science in general, in which there's just a lot of interest in data science. A lot of companies are trying to turn to data science to understand what's going on at the company. They're collecting tons of data now. Like pretty much every electronic device is spewing out data at this point. And so a lot of people are trying to use it to make their lives better, to make better decisions. And machine learning is just kind of a really key component of what is known as modern data science. And so a lot of people also gravitate towards it because it's just kind of, it's the flashiest part of statistics and data science to a lot of people. Nobody wants to go and learn how to, check their standard errors on a regression model accurately in the presence of something boring like heteroscedasticity. But, if someone comes and tells you that they have this crazy new algorithm which mimics the way that the human brain works and can detect any pattern you want in an unsupervised learning, like there's so much more flash factor with machine learning than kind of traditional statistics that I think a lot of people are just drawn to it. And so a lot of people, even who haven't like really done the core of statistics that you need to validate these models that are put out by machine learning algorithms, are jumping into the field. And it can be a little dangerous because you have people who are using it who might not be as familiar with the techniques to know whether it makes any sense or not. Something else I just wanted to say is, with the unsupervised learning example, I think another important distinction is if you're dealing with data for which you don't know the answer. That's a case in which you usually want to use unsupervised learning. So for example, if you had a bunch of credit card transactions, but you actually didn't know which ones were fraud and you wanted to look backwards, sometimes you need, because you just don't know the answer, you have to there's no way to supervise it. You can't say this is fraud, this is not fraud, this is fraud, this is not fraud. But if you had examples of credit card transactions which were grouped into stuff you knew was fraud historically and stuff you knew was not fraud, then that's a different situation, and you can do different types of stuff with that.
Okay, sure. So even with the flash factor, does machine learning bring anything new compared to traditional statistics methods?
I think it absolutely does. And the way I view machine learning is it's like machine learning is really kind of like a gun. It's really powerful when used correctly, but it's also really easy to do serious harm to yourself if used improperly. And the serious harm, of course, is if you have a machine learning algorithm and it spits out something that looks really good, which machine learning algorithms will tend to do. And we can go into this a bit more later, but machine learning algorithms are really, really good at fitting data. And so they're really, really good at overfitting if you're not careful. And as a result, oftentimes if you apply machine learning to something, you'll get models that look so good on the data set you trained them on. They look like perfect. They can predict everything that happened. And as a result, you get this amazing confidence in your ability to predict things going forward. And of course, just like any other statistical method, if you haven't done your proper validation, you could completely fall apart out of sample and blow up. And of course, in finance, that's a particularly big risk because it could be that you lose a substantial amount of money. But that said, the kind of broad power that machine learning algorithms have to deal with new types of data do bring a lot of new things to the table in finance. And I think that there are some really good uses of machine learning in finance and some dangerous uses. So some of the stuff we're going to talk about as we go on today is what some of the broad good cases are, and some of the broad maybe you don't really want to use it this way cases are. And so maybe we could just start with an example. Which I have a fun metaphor all ready to go and talking about unstructured data.
Go for it. Yeah, well, let's go into some of those good usages and poor usages of machine learning. Like when is it powerful and when is it not so much?
Yeah, so I'm going to give a shout out here. So one of the first professors that we ever worked with at Quantopian, his name is Andrei Kirilenko, and if you Google search him, you'll actually find a Russian professional basketball player. So you have to Google search Andrei Kirilenko finance or something. But he's a really smart guy. He used to be the chief economist at the Commodities and Futures Trading Commission here in the U.S. And was teaching at MIT when we met him. He's now actually running a new program, I believe, at Imperial College London, which I recommend if any of your listeners are in London and interested in some kind of finance program. I definitely recommend you check it out. He really knows this stuff well, and one of the things that most impressed me was just how much he focused on this statistical rigor when he was teaching, because he was teaching a lot of people who had heard about these crazy new techniques, who did want to do this stuff. And he was really good about making sure that, they came away with good and bad examples. And he had some good, kind of very visual stories of explaining some of these concepts. And so I'm going to use one of his right now, which is there's a preponderance now of what I call unstructured data. And what that means is you get data that really has no no structure to it. You're getting data. An example might be headlines, news headlines, right? There's no structure of a news headline. Every reporter writes theirs differently. There's going to be structure in the language. Let's say that you're looking at just English news headlines. Well, there's going to be structure because English has a structure. But beyond that, that even might be pretty weak because news headlines use a lot of slang. They use a lot of shortening. Like headlines have their own language, right? They kind of drop words as appropriate to fit the headline onto the page. And so you're looking at a headline and you're trying to learn information from those headlines. The metaphor that Andrei Kirilenko likes to use for this is imagine that your data source is the garbage that's coming out of a coffee shop, right? So you're in the back alley, and every time they dump their garbage out, you take their garbage and you're trying to learn as much as you can about the workings of the coffee shop from the garbage. And this is actually a really good metaphor to understand how not only unstructured data often is, but kind of how machine learning algorithms can oftentimes be powerful. Because what you have there is well, what are you trying to learn about? Well, let's kind of try to get a sense of what data you might have. You're going to have obviously like coffee cups, and maybe you have different coffee cups because they have different types of cups for different drinks. They might have paper cups and plastic cups, and they have different sizes of cups. And some of the cups will have a name written on them, and some of the cups will not have a name written on them. Some drinks are served in 2 cups, and some drinks are served in 1 cup. They'll double up the cup sometimes. Some cups come with one of the cup holders so you don't get burned. Sometimes you'll have a lid attached to the cup. Sometimes you'll have free floating lids. Sometimes you won't have a lid at all for cups. So you can get a sense, and of course that's all floating in a whole other garbage, right? So that even like information you might want to get at, like stuff like what type of cups you're looking at, trying to reverse engineer what type of drinks the coffee shop is serving. Let's say that's all floating in like a whole bunch of other garbage from like food or napkins or whatever. So you're sitting there, and this is actually really close to when quantitative professionals, whether they be in finance or other fields, are looking at unstructured data that's flowing in from the real world. Oftentimes you need to do a data processing step. And so a huge part of modern kind of data science, and oftentimes what will set apart someone who has data science on their resume from like someone who says statistics, is this notion of cleaning the data and getting the data into a usable format. And that would involve sorting out your garbage, and okay, now you have a pile of cups, and then you start counting the cups, and you make notes of this cup came with another cup, this cup came with a lid, this cup came with a name. And then that kind of data, which isn't necessarily all the same format, you're going to have a lot of null values in there, lots of different weird stuff. This is where machine learning can be really powerful in getting you somewhere useful, because what machine learning methods will do, especially the unsupervised ones that Max was talking about, is they will kind of from that be able to start giving you initial ideas about the broad trends that might be present. What you can do is you can start saying, look at each individual piece of garbage and try to classify it as one thing or another based on this, learning that you're doing. And this is the type of situation oftentimes that machine learning is very powerful at, because a lot of the algorithms are actually designed to work in these kind of unstructured data scenarios.
Okay. Is there anything you want to add on to that, Max, or should we keep moving?
Yeah, I think that's a delightful example. Sometimes your cups are actually forks.
So let's continue on this point. What are some good usages and also some poor usages of machine learning, like in a trading sense, in a finance sense?
I'll quickly give one more kind of follow on. So I think we actually probably talked about this before, but like the favorite example, and I'm pretty sure you talked about this briefly in one of the previous episodes, is using computer vision to analyze images, namely satellite images, right? And so if you have satellite images of parking lots and you use computer vision, which is oftentimes models that are trained using some form of machine learning, you'll have like these classifiers that look at these images and they attempt to first of all, catalog, split the image into objects. That's one of the problems. And then the next is for each object, classify it as a thing. And this is actually a problem that we've gotten pretty good at. Google especially has been one of the companies that's like really, I think, been ahead of the curve in designing computer vision technologies. And so as a result, nowadays we actually have open source computer vision libraries that actually work pretty well for just saying, this is a car, this is a cat, this is a person. And it's because they've just trained these models on like so many tens of thousands of examples of things that are people and things that are close to looking like people but are not people. And the algorithm has learned the rules for differentiating the two. And so what you can do is you can take these models that have been developed and apply them to these images and count how many cars are in the parking lots, and then use that to try to forecast sales figures for retail chains. So that's an example of taking, unstructured data, which is in the form of images, and turning it into an actual score, which is like cars outside each retail chain for each quarter.
Okay. So what would be a poor usage of machine learning in a trading sense?
We mentioned a little bit about how it's really easy to overfit with machine learning. And one of the very fun things about financial data, especially like price data, is that it's really, really noisy. It's jagged, it's ugly, it's contorted, it doesn't follow any nice assumptions. So why not just forego the assumptions entirely and use a machine learning model in order to predict prices? The issue with this is because machine learning models are so flexible and because they're so good at fitting the data, they'll contort exactly to fit this noise. And then going forward, whenever you have any sort of process in real life, so whenever you have any sort of process in real life, there's always some true underlying thing driving it. There's some underlying process that makes it all work together. And whenever you build a model, you're trying to infer that underlying process from the data at large. But if you fit perfectly to the data, since it's real life data, there's going to be a lot of noise involved. So you're just contorting it to fit what you actually see instead of getting any actual information about what's actually there. So when you then go out of sample and try to use this in order to predict any sort of future prices, it's just going to be garbage.
Okay. Is there any way you can use it to predict or attempt to predict future prices without it being garbage? Like, is there a way that it can be used for forecasting prices, or is it best used in, the examples we've talked about, like, if you want to use satellite imagery as an example, like actually using it to read images?
So I think that it certainly can. I think that would probably be considered like the most advanced use case of machine learning in finance. It would be actually using it directly as a price forecasting model. And that's just because, again, I think that given like the problem you're trying to solve and the nature of the data and the system producing the data, that's just the riskiest application. And so you need to have kind of the best experience and steadiest hand to be able to do something like that. So I would say that would not be my recommendation as the first place to start playing with machine learning in finance. Although I think for a lot of people, it's the first it's the most intuitive place to try to use it, is just to predict prices, because that seems like the best idea off the bat. But I would actually say that's kind of probably one of the last places you want to try using it, and not in the sense that it's not going to work, but in any individual case, I don't know if it's going to work. I don't want to tell you that these things are going to be like definitely bad or definitely good. What I do want to say is just like, you want to apply the same model validation principles to whatever the machine learning algorithm is spitting out as you would to anything else. So a lot of the stuff that we talked about in the first episode, when we talked about biases and ways to be wrong without knowing you're wrong, you want to watch out for those same things with machine learning, and for machine learning, some of those are especially common. So I'll give you an example of something that I might do here, which is, let's say that I had a data file of 60 variables that I was recording all the time, and I wanted to use these 60 variables to predict the price of some stock, some asset. And so what I might do is I might use machine learning to basically try to guess some variables that might be good variables to use in a model to predict price of this asset. So the machine learning algorithm would look at my data set of 60 variables going back in time. It would look at the price of the asset that I wanted to predict, and it would try to come up with some set of variables, hopefully a smaller set. It would try to come up with maybe like 5 variables, 2 to 5 variables that predict the price of my asset. And this use of machine learning is known as dimensionality reduction in data science, and it's especially common in a field where I used to work, which is bioinformatics, in which you have millions of genes, and you want to figure out which genes are associated with diseases. And so you just can't look at all the genes at once. So you need to use filtering methods to filter down to small sets of genes for kind of more in-depth analysis. And yeah, you might throw the good ones out when you're using the filtering method, but that's just a risk that you're going to have to take, because if the amount of analysis you can really do is in maybe like 20 genes maximum at a time, for a variety of reasons, statistical and computational limitations. So if I have like 60 variables and I'm trying to predict the price of some asset, I might use a machine learning algorithm to filter myself down to a set of, say, 5 variables, and then construct a simple model based on those 5 variables, and from there on just validate it the same way I would anything else. So in this case, I'm using machine learning to try to inform my model selection, but the model itself is still a very simple model, probably just like a linear regression, a linear combination model or something like that. So that's an example of how I might go about using machine learning to try to forecast price. Although obviously, like in any individual case, I have no idea if it's going to work.
Okay. Now you said something towards the end there, which I think might be key. And I'd love it if you could expand on that a little bit. How important is it to try and keep the model itself simple? Like even when using machine learning techniques, is it like how important is it to keep things simple?
So simplicity is kind of like the crux of everything that you're trying to get at with a model, because you want it to be general is the idea. Like you want it to be trained well on the data that you already have, the things that you know about, but you want that model to be general enough to still be extensible to any sorts of new information. Like this is part of the issue with like fitting to noise that I was talking about before. Like if you're fitting to the noise of a very particular data set, of data that you already have, that noise is going to be different in the future. It's going to change. So if you're incorporating the noise as an integral part of the model, if you're making it more complex as a result of the noise, you're making your model less general. So there's actually a bunch of different methods in order to kind of determine whether your model is too complex or as simple as it could be. And it comes down to a lot of the same things that we use in like normal statistical models. Because this is something that we want to look at with normal statistical models as well. We generally want general models that are relatively simple and explain as much information as possible with as few terms as we can. So we'll conduct a lot of testing with our machine learning models in order to kind of penalize any sort of complexity, to rein in any sort of extra complexity so that they don't go off the rails or do anything weird.
Okay, I was just going to say like kind of 2 points. One, just to circle back to points we made before, out of sample testing is really important, because without like if you come up with some model, even if it seems simple, unless you have saved some of the data to test on, like your model is going to be built on the data you've already seen. So of course it's going to work well on the data you've already seen. It's like if you teach someone to drive on a small section of roads in one small town, yeah, they'll get good at those roads, but then when you let them loose on like a highway, it's not going to work very, very well. So, you generally want to make sure that when you're actually evaluating your model, you want to use data that you have not seen before, preferably new data that you've kept separate purely for the purpose of testing your model. And then as soon as you see it, it stops being out of sample data anymore. Now, you've seen it, it's done, it's used. So that's just an important principle that I think is still required when you're doing any kind of statistics, especially machine learning. And, there are some people who might argue that out-of-sample testing is not always strictly necessary. And I would say that if you're at a point in your statistical knowledge when you can argue that with me, you don't need my help. You can go off and do whatever you want. And then the other thing is just really like, in terms of like model simplicity, again, like the goal of models is really to be as simple as possible, because if you look at what physicists are trying to do when they're trying to explain the universe, right? They're looking for like very simple, broad explanations that capture large amounts of behavior. And all like basically like nobody in physics tries to come up with a model which is based on 300 variables and precisely explains the motion of some asteroid, because most likely that model is going to be wrong for reasons of overfitting. You just can't check it. You have so limited data in general. The more variables you have in the model, the more complexity. You actually need exponentially more data to check whether that model makes sense. So as a result, physicists always try to come up with models that have like 1 or 2 variables, very simple effects, and explain a wide variety of phenomena. And then you can explain very complex phenomena by building together multiple simple models into complex systems. So that's just like a really important point that I think is important to remember with all this stuff. Whenever you're trying to think about ways in which you might know more than the market and test those, you always want to be finding kind of broad behaviors that are expressed by some simple rules. And the opposite of this is what's known as black box models, which is something we can talk about a little bit more later. But a black box model is just a model in which you don't actually understand what's going on inside. And could be anything, but you can see the input and output. And those models tend to be very risky. And a lot of machine learning algorithms actually spit out black box models that really can't be comprehended in any way. They just have inputs and outputs. And those models are very risky because you just have no idea what's going on inside there. You don't know how many variables they operate on. You don't know why they're making the decisions they do. And there's just no way to validate it.
So do you want to talk about why that's an issue with black box, quote unquote, systems? Like it probably seems quite obvious to, you guys, but like for someone who might be sort of new to this sort of thing, why is that dangerous to not really know what's going on inside your black box?
So part of having a model is you want it to tell a story about your data. So you want it to be in some way understandable by the people that are trying to use the model, because that makes it comprehensible. If you can explain the model, it means the model likely isn't doing anything bizarre or weird or uncouth that you wouldn't necessarily want a model to do. So if you have this black box that you're just putting stuff in and putting stuff out, again, it goes back to the same idea of overfitting, where even if you're doing well in your out of sample data, you may not necessarily know why. And a lot of times when we're dealing with these models, we want to know what's the most important stuff. What are the key driving factors? And if you can't explain what the key driving factors are in a model, then it just makes the model just kind of fundamentally less helpful, even if you do get the correct answers in the end.
Now, Max, you've spoken about there being a lot of noise, especially in price data. You've brought it up a few times. I'm just wondering, is there any way that you can sort of separate noise from signal, if that's the right term, when you're looking at data? Like, are there any methods you can use to kind of separate the two?
So it's hard to separate the two directly. Basically, how we kind of immunize ourselves against these mistakes of dealing with overfitting and dealing with too much noise is like we have our out of sample testing, but in some cases, if we have like too few data points to do out of sample testing, like machine learning models tend to require a lot of training, a lot of data in order to inform them. So we can't really break it into like an 80%, 20% split where we're testing and building our model on 80% of our data, and then we're taking that model and then using it on the out of sample holdout 20%. Sometimes we just don't have enough data for that kind of stuff. So what we'll do in this case is something that we call cross-validation, which is instead of doing one split, we'll do 2 splits or 3 splits or 4 splits or 5 splits, or just however so many splits as we desire, depending on how uncomfortable we are with our small amount of data. And what I mean by a split is we just like, say we have 100 data points, right? And that's all we have to work with. Then what we do is we'd say, hey, we want to do 5 rounds of cross-validation. So we would in turn take 20% of our data and then take 80% of our data and train that and then test it on the holdout 20%. Then we pick a different 20% of our data. And we just keep shifting this block of data that we're training and then testing on in order to kind of simulate a larger amount of data and try to go from there to try to alleviate any effects of particularly noisy data, which can only be aggravated when you have fewer data points. Because when you have more data, it tends to smooth out this noise.
And what you're looking for there is consistency. You want your model to consistently explain what's going on through all the different rounds of training, testing, because if it stops being able to explain stuff consistently, if it picks kind of different patterns each time, that's an indication that it's not really picking up anything consistent in your data set, and therefore all it's picking up on is noise. I view kind of cross-validation a little bit as kind of like poor man's out-of-sample testing, in that, you know, it's not optimal in many cases, but it will help in reducing the risk of overfitting. I think in general, it's really hard to split noise from signal, because if you could split noise from signal, you'd know exactly what the signal was, and therefore you'd have the answer already, if you were able to do that. I mean, one of the simplest ways you can try to get rid of noise is by increasing your sample size, and then, you know, averaging everything together, you know, because if the noise is kind of going in both directions randomly, and then you average 2 things together, you know, there's a higher chance that noise will cancel out. And if you have 100 things and you average them all together, there's a higher chance that noise will cancel out. So oftentimes, just looking at more data is usually a way to try to get rid of noise. Sometimes, though, you're constrained into systems in which you have a fixed size. There's only a fixed number of assets on the US market. You can't like get more data. You know, you can't really get more assets per se in that. So you don't always have that luxury.
Yeah. Now, that's a really good point. So I think this has been a really good overview of machine learning. I'd just like to spend a few minutes and maybe talk a little bit more about how to actually go about learning and maybe implementing some of these things. Does the Quantopian platform support machine learning? I know you mentioned earlier that it does take quite a lot of computational power. Are there any limitations on the Quantopian platform in regard to the use of machine learning?
Certainly. I mean, we currently have some limitations on the platform. However, and we'll link to these examples at quantopian.com/chatwithtraders. We'll have content for all the episodes listed out. And for the machine learning episode, we're going to link to some examples of actual implementations of machine learning for, I believe, factor aggregation, which is something we talked about in the previous episode. So using a machine learning algorithm to try to construct one overall factor from a variety of input alpha factors. And I'm actually not sure of the second. I think the second one is actually using it as a factor itself, as a price forecasting model. So the thing I said was the hardest, kind of most dangerous thing to do. So those are both examples made by mostly Thomas, I believe. I'm not sure. Did you take a look at those, Max, or is that mostly Thomas in his cave who pumped those out?
Yeah, that was Thomas and James.
Thomas and James. So Thomas and James Christopher. But so we'll have examples listed for actually like how you would do that in the Quantopian platform. Currently, it's kind of hard to actually put the machine learning methodology into a trading algorithm, but within our research environment, which is kind of offline analysis and hypothesis testing and statistics, you can do actually quite a wide variety of machine learning stuff. Nothing that's going to take like, there's some algorithms that just take like huge amounts of memory and computational time, and those currently you can't use. But a lot of the machine learning algorithms, just because consumer hardware has gotten so fast these days, actually run fairly quickly. And so you can do some pretty advanced stuff as far as, you know, a lot of the cases that I was talking about, like, you know, looking at trying to parse unstructured data or select factors for your model or aggregate alpha factors, that kind of stuff. And we're working constantly on trying to enable more support for more types of machine learning and just other use cases on the platform.
Yeah, I know I'm going to be working on lectures teaching machine learning at some point. And just as part of our research environment, we allow you to use scikit-learn, which is a very popular package in Python, which has just a very large number of classifiers, estimators, and their documentation is really fantastic, and it's a good place to get started with learning how to actually use the methods.
Yeah, I was going to ask you about that actually, because scikit-learn is the main library or package for Python for machine learning, right? Are there any other packages or libraries that you'd suggest for this as well? Or is that probably enough to get started at least?
I mean, I know there are. I don't know off the top of my head. I'm not someone who I've done my time in the machine learning mines, but I'm not currently using this day to day. And Python moves so fast that I'm sure that since I've touched it, there are many libraries that have popped up which do tons of interesting stuff with machine learning, tons of forks of various other libraries, and there's so much work going on right now in Python. So I couldn't tell you right off the top of my head if there are other libraries. Max might know a few others that are good, but I think scikit-learn also learn. What is it? What's the module is actually sklearn. So I think some people probably know it as like sklearn. I think is like the flagship library in Python that really will get 80 to 90% of your use cases done out of the box.
Yeah, but there's TensorFlow, but that's a little weirder.
Yeah, there's TensorFlow, which is like a whole new
world.
We're talking about hype cycles. There's this little mini hype cycle going on around tensor computations, which are used, I believe, for calculating covariance matrices, which I'm not even going to get into right now. But that's like a whole little subfield of machine learning that has popped up, especially in finance, because covariance is so important, especially for portfolio construction.
Right. Okay. We'll save that for another day. There's also a course by Andrew. I'm not going to attempt to pronounce his last name either.
NG.
Yes. Yeah, that's how it's spelled. Is that how you pronounce it?
You pronounce it "ng," I think, okay. But I'm doing a very poor job at that. So please don't write me hate mail. So that's my pronunciation that I use in Singapore, and it's close enough that they've given up correcting me on it. Okay. So
well, that's
just a couple
thing.
Yeah.
Yeah, I know his course is very sort of highly rated in the field of machine learning. Is that something you guys would recommend people check out if they're interested in learning more about this? Would that be a good place to start also?
I don't know the course. I don't know. Max, do you know the course?
I started looking into it.
You started looking into it?
Yeah.
I don't know the course. I know he's very highly regarded, and he is kind of the go-to name right now for machine learning. So I would say my Bayesian prior on this is quite strong that it would be a good course, but I cannot actually endorse the course, having never seen it myself.
Yeah, I like the stuff that I did read.
Sure.
Okay, cool.
You've got a small sample, very small data sample from Max.
A very partial.
That's funny. So is there anything else you guys would like to add on machine learning before we wind things down here?
I mean, honestly, if this stuff fascinates you, just try messing with it in Python or your language of choice. I say Python just because obviously that's what works on Quantopian, and I think in kind of also in a more objective sense, it's the easiest one to get started in.
Yeah, scikit-learn makes it really easy.
Yeah, and also Python is so good at ingesting data, whether it be unstructured data, scraping web pages, parsing text files, whatever you're trying to do, Python actually makes it pretty easy. So it's generally a good place to start. But obviously, if you're experienced and you have some programming knowledge, some math or stats knowledge, just try it, because this stuff is cool. And the reason it's cool is why it makes it so dangerous, because you want to try all these complicated models, and then you're like, oh my gosh, this thing actually works. I'm going to make billions of dollars, and it doesn't. But just go try it, and we'll have links to a lot of the related content for stuff we talked about at quantopian.com/chatwithtraders under the section for this episode. So you can actually start trying to play with it a bit.
Awesome. So the next episode is going to be a Q&A episode, and that's going to be part 6 of the series, which will be the final episode. So For that, we're obviously answering any of the listeners' questions. So, guys, if you do have a question, and I just want to emphasize that there's no such thing as a dumb question. So, no matter how basic it may seem, don't be shy. Please do ask it. Where is the best place, Delaney, to submit those questions?
So we'll have a link set up by the time this episode goes out. If you go to quantopian.com/questions, we'll have a form there. You can put in any question you want, and you can just we'll take a look at them and answer as many as possible, especially if we find ones that have, the same question as many other people, because that we get the most bang for buck. But if we don't get to your question, I'll try as hard as I can to also, even if we can't get to it on the podcast, maybe make a forum thread and respond to it in the forum thread or something like that. So I really will try to get to everybody who asked a question, which I know the listenership of this podcast is quite broad. So I may be biting off a little bit more than I can chew here, but hopefully we'll get some good questions.
Yeah. So guys, please go to quantopian.com/questions. The idea of this is that we can just collect all the questions in one place. So, we're not collecting some on Twitter, some in forums, some in comments. If you do have questions, go to quantopian.com/questions. We can collect them all in one place and make sure that none get lost. So, I think that brings us to a close for this episode. Max, thanks very much for joining us, man. It was a lot of fun.
Yeah, thank you for having me.